Hello. So I'd like to talk to you about an HTML widget that I've been working on. So this is a widget for exploring high-dimensional datasets, high-dimensional numeric datasets. So it can generally be invoked from R, either directly in R or RStudio, or maybe as part of an R Markdown document. But then the heavy lifting happens in JavaScript, so all the interaction and all the calculations. And that lets us have a very interactive and high frame rate widget. So what this is doing, we have a high-dimensional data set, and it's showing projections of that data into 2 dimensions. In the mode it's currently in, it's spinning around randomly. We can also switch it into a guided tour mode. Then this seeks some sort of optimal projection, where optimal could be fairly arbitrary. I've got some sorts of guided tours already implemented, but there's a lot of space to implement more of them. And it never quite settles down to a particular projection. There's always a little bit of movement, and that's giving you a bit of information about all the dimensions of the data. So there's also a few ways to interact with this. I'll get to them throughout this talk, but I'll start with one that you can hover over different groups in the data to highlight them, or hover over variables in the data to see what values they have. And I can also hide particular groups, and then the display adjusts to find a good projection of what is currently visible. So show that again, adjust back. Okay. So what's going on here? Langevitour is a bit of a new take on tours. Tours in the past have generally involved generating a sequence of distinct projections and then doing a nice interpolation between them to animate the tour. There's various pieces of software that do this, like Xgobi, Ggobi for desktop applications. Tour is an R package. And that sort of has a lot of the architecture you might want in a tour package, and then there's various other packages building on tour. However, langevitour is a bit of a new take. It's rather than having a distinct sequence of projections, it's using something called Langevin Dynamics. This is more like a sort of physics model. Produces a smooth random path with sort of the properties that we want. So the arm waving version of Langevin Dynamics. I don't really want to show you stochastic differential equations in a 20-minute talk. The state of the system consists of a velocity vector and a position vector. In this case, the position vector represents a particular projection matrix, which we'll use to display our high-dimensional dataset. And so the position is changing based on the velocity, and then the velocity is being updated by various things. So there's always noise being injected into the velocity to stop the velocity therefore becoming very large. We also have some damping, and if the guided tour mode is activated, there will be forces based on the position, and they will change the velocity. Now, just a further complication here. We want our position to always represent a valid orthonormal projection. So what we really want is a constrained physics engine. So Langevitour uses something called position-based dynamics. What that involves is first we do a velocity update, then we do a position update. So far that's a leapfrog sort of numerical simulation. And then we fix our updated position, so find the nearest valid orthonormal projection, and then we fix the velocity to be consistent with the actual step in position that we've taken. Okay, so what's going on with these guided tours? So the app will sample projections near some optimum, and that optimum is defined by a potential energy function. So we consider low energy states good projections and higher energy states not so good projections. And neat thing about Langevin Dynamics, it really does sample from a distribution, and from the distribution we specify with this potential energy function and also with the temperature. So that's super cool in all sorts of ways. Now, and so the path there, it'll be a nice smooth path, it's nice to look at, but then in the longer term, it is actually sampling from this distribution and is sampling from the distribution quite efficiently as well. So when it comes to implementing this, the force applied to the velocity is the negative of the gradient of this potential energy function. So we need to be able to calculate the gradient. So in particular, what I've implemented so far is a potential energy function based on the distances between each pair of points. So this has the effect of sort of creating a repulsion force between the points. So it'll spin around the projection to spread out the points. So I want to turn now to an example, sort of in my own line of work. So single cell RNA sequencing. So this is where we count RNA molecules in a biological sample. And those RNA molecules come from thousands of different genes in usually tens of thousands of cells, something of that order. And we are able to, for each RNA molecule, identify the gene and identify the cell. And so with a little bit of processing, we get a big matrix of counts, generally a fairly sparse matrix. So now, in particular, I'd like to look at a PBMC dataset. This is sort of the classic thing that people look at with scRNA-seq. And so this is immune cells extracted from blood. So T cells, B cells, monocytes, that sort of thing. And then typical processing steps here. I'm using Seurat. There's a few different pipelines for this. We would normalize, so like the total count within each cell is about the same. Log transform, doing something a little clever about the zeros, and then find principal components. And then very commonly people would go on to do a UMAP layout based on some number of principal components. So taking those principal components down to 2 dimensions in a non-linear way. So this is usually pretty effective. You can see it's nicely clustered. The points here are cells and they're clustered into cell types pretty nicely. But maybe UMAP is sort of obscuring a bit of what's going on here. So one thing here these red dots are what's called doublets. They're actually mixtures of two different cells that the machine for doing this single cell sequencing has sort of lumped together accidentally. But you can see in the UMAP they're sort of stuck quite closely to particular cell types. Sort of, I want them to be more spread out because they really are between cell types. So now let's look at this in Langevitour. And so it's quite a lot fuzzier. So this is the Grand Tour mode. We could sit here and sort of soak in the structure of the data a bit. Or maybe we can go to sort of guided tour mode. And it tries to find a nice layout of the data. Though possibly not quite as nice as the UMAP. We could sort of look at the doublets and notice this is far more of a linear view of the data, and the doublets are more spread out, and they are actually between cell types. We can also see the monocytes are sort of more spread out than other cell types. That's another thing that the UMAP erased. So now this is still quite fuzzy, so what I like to do is a denoising step. So trying to preserve the structure of the data, the geometry of the data, but dial down the noise a little bit. So what I'm doing here, for each cell, I find its 30 nearest neighbours, and then their 30 nearest neighbours, and set the cell position to be the average of all of those cells. Now, you can see, looking at the doublets again, they are still sort of between cell types, so it hasn't erased that. But maybe looking at the overall structure, it's a bit clearer. Turn off doublets, and sort of now fairly clear what's going on. We could dig into this a bit further. Okay, like most of the layout here is the distinction of monocytes from other things. So maybe if we turn that off, the display changes a bit. You can see a bit more of the structure. So you can sort of play with it like that. Okay, so now that's actually half of this data set. So we've got immune cells, and then a portion of those immune cells were treated with a cytokine, recombinant interferon beta. And this causes the cells to get ready to fight an infection. So their gene expression will change. They'll be producing slightly different RNA molecules, which will then be used to produce proteins that get them ready to fight. And so, okay, so here darker is unstimulated and lighter is stimulated. And you can sort of see in the UMAP there's this pairing up, but the UMAP is non-linear, so we can't really see. I mean, you can see something, it's sort of hinting, but it's a bit unclear what is really going on here. So, looking at this in Langevitour, so we can see sort of unstimulated and stimulated cells of the same type. They're sort of parallel to each other, and we can even sort of dig around and see what is driving this. So now these are Varimax rotated principal components, so they are actually somewhat interpretable individually. And so we might notice component 3 seems to account for most of the differences. You can drag that onto the plot and have a look. And then if we hide component 3, notice most of the cells are now sort of overlapping between unstimulated and stimulated. But there's still something going on with the monocytes. So we could sort of dig around some more, have a look at other components, and notice. So C1 seems to be, well, it's basically, is the cell a monocyte? And then C2 is some specific response to that cytokine in the monocytes. So you can play around and really dig out what's going on in the data. So now I want to show you another slide to go with that. We've been looking at the cell scores so far. We can also look at the gene loadings. These will, for the same set of components, we can see what genes are involved. So this is a bit less structured than the cells. We can clearly see cell types. With the gene loadings, it's more of a sort of spiky ball type of thing. So we were looking at C3 in particular. And so what varimax rotation does is all these spikes in the loadings, it aligns to a particular component. So we can see C3, it's this particular spike in the loadings, and we can sort of see the genes involved there. We might look at that C1 and C2 that were involved in monocytes. There's this sort of interesting fan of gene expression between them. Or maybe we just want to look for outliers. So I have a special guided tour mode that looks for outliers. Maybe I'll turn up the force that's applied. This mode's a little bit prone to local minima, but yeah, it's finding some fairly convincing outliers there, especially this C10. I think those turn out to be to do with the red blood cells. There were a few red blood cells left in the sample alongside the immune cells. So yeah, this is another side of the data that we can also dig into with Langevitour. Okay. So summing up, Langevitour lets you sort of soak in the structure of your data, and then you can sort of switch to actively exploring it, pulling out particular groups or particular variables. And sort of as you pin down the projection you want to sort of get at the thing you're interested in the data, it never stops moving, and that those small motions are an extra channel of information. It seems to be a channel of information that our eyes are pretty good at interpreting. It's a very natural sort of motion. It's actually, I find it enjoyable to look at. And yeah, it's giving this extra information that you would not get in a static image. So in particular, I was interested in single-cell RNA-seq. Sort of a concern we have with this sort of data is it's very complex methods we're applying to high-dimensional data, working out like what are they doing? Are they doing what we want? Is sort of a question that nags a bit. So it's nice to be able to look at that in a fairly honest, linear sort of view of the data. So here, for example, here's a method that removes differences between samples. This example removing differences between unstimulated and stimulated cells. From this you can see, yes, that does appear to be doing what it should be. Okay. As I said at the start, you can use this directly in R or RStudio as an interactive tool, or you can output it as a static HTML document using R Markdown. You can share that with your friends as a file, or put them on a website. If you want to publish them, if you're publishing in the R journal or Distill, you could probably have them as a figure. Other journals, maybe you would need to put it as a supplemental file. So that's the widget. I should say, so the start of this idea came out of some discussions with Di Cook and Stuart Lee, as Stuart was working on his PhD. I knew what this app had to, like, how it should basically work, but that idea sort of choked away in the background for a few years until I happened upon the word Langevin Dynamics, and with that clicked, and like I could look up material on Langevin Dynamics, and that really made it come together. And so yes, the code came out. So that's the widget. Thanks for listening.